Okay, so welcome to today's robotics lecture. So do you have any questions about the homework for inverse kinematics? Or you have already solved the problem? So I'll give the solution in this weekend, so you can check whether, if you have any problem with the homework, then you can check with the solutions. So today's topic will be Robotics and differential kinematics. So last week was your proposal presentation, and today we'll be introducing the Jacobian and the differential kinematics, and also we'll have three groups for the case study presentation. And we still have, next week we still have one lecture about the statics and stiffness analysis. Then will be your midterm exam. And next week we'll have a very quick review section about your midterm exam, so you know what are the topics you need to study for your exam. And if you can do your homework and you can solve all the like forward kinematics, inverse kinematics, then the exam is definitely much easier than your homework. So if you know how to do all the homeworks, then I think it's fine for your exam. So today we'll be coming to the differential kinematics. So like from here is the introduction, and here we introduce the components that we need to design a robot, the sensors and the actuators you need to choose. And then this topic comes to the robot modeling. So start with the position and orientation and the homogeneous transformation. And these two are the position analysis. Then differential will be the velocity analysis, and the statics is the force analysis. And these two are the application for the robots. So this is just a quick recap. So I think most of you are already very familiar with this diagram. So this is the reference space, and this is the reference frame for the aim factor. So what we want to do in the robotics is we want to know what is the orientation and the position, or you can call it pose, of the aim factor with respect to the base frame. So in robotics, we just interested about this problem. And so from the joint space to the Cartesian space is forward kinematics, and reverse is the inverse kinematics. And you can see if we want to map the joint position to the A factor's configuration in Cartesian space, then it's forward kinematics. So today we will map in the velocity, so from the joint space. So you can the joint velocity to the A factor velocity in the Cartesian space. So the matrix between them, the relationship between them is called the Jacobian matrix. So this is the Jacobian matrix. So the definition is the relations between motion or the velocity in joint space and the motion in the task space, or you can call it the Cartesian space. It's the XYZ. And the instantaneous velocity maybe can be obtained through time invariant of the direct kinematics, the forward kinematics, or in the geometry directly at the differential level. So there are also two methods you can obtain the Jacobian matrix. So the first one is the analytical Jacobian. So it's obtained by time differentiation, so or derivatives. So this is your forward kinematics, the solution. Then you just divide it with the time. So you divide with the angle or the displacement, the theta first, then the theta divided with the time. So you have the q dot, which means the angular velocity of the joint angles. So by this way, you can map the joint angle velocity to the n factor velocity. So this is called an analytical Jacobian. And the second method is the geometric Jacobian. So in this, we directly find the relationship between the velocity of the joint and the velocity of the n factor. And we were told you how to find these matrices afterwards in this lecture. So in both cases, the Jacobian matrix depends on the current configuration of the robot. So if you have the same robot, but in different configuration, then your Jacobian matrix will be different. So it's not like your forward kinematics. You have the same matrix for all the configuration. The Jacobian matrix depends on the current configurations. And this is a quick recap for the dynamic if you have learned it from undergrad. So we know that the angular velocity of a rigid body, so this is the V, or the angular velocity of a rigid body. So this is the omega. Omega is the rotation velocity about this axis. So this is involved, so because it's a vector. And cross RP is the radius. And we can also say that if there are rigid body, if they have two points, point A and point B, so the V AB is equal to omega. This is the angular velocity omega is associated to the whole body and times the vector, position vector between them. So if VA equal to VB equal to 0, then will be pure rotation. So it is a circular motion. And if omega equal to 0, then it will be pure translation. So it's just moving in different positions, but not the rotation. So this is just a quick review for dynamic. So the n factor instantaneous velocity, we can write it like this. So this is the translation and this is the rotation. This is the translation velocity and this is the rotation velocity. So by mapping, this Q dot is the velocity of the angle, and this is the velocity of the n factor. So by the diagram, we can see if you have a robot, and this is your n factor. So this n factor is moving at so this is the translation. And this is the rotation. So this n factor is moving and also have a rotation. And each joint is rotates as Q dot, or you can say Qi. This is Q3, Q2, and Q1 dot. So these are the angular velocity, and this is the velocity of the translation and velocity of the rotation of the ending factor. So what is this measures? Or what are these matrices? So this is the Jacobian matrix mapping the q dot to the translation velocity of the ending factor, and J is the Jacobian of the angle. It's mapping the q dot to the rotation velocity of the ending factor. So if you extend, if you have like n joints, then you have n joint velocity, and you will also have 1 to n Jacobian to map between them. So this contributes to the linear motion of the ending factor velocity. So VE is equal to Jacobian times Q1 and power plus n Jacobian times Qn. And this Q is it's the angle of the robots at this current configuration. So it's not a variable. It's like if Q1 equal to 30 degree, Q2 equal to 30 degree, and Q3 equal to 0 degree, just for example. And so if the value of the angle is different, then the Jacobian will be different. So it depends on the current configuration. And the linear and angular velocity belong to the vector space in 3 dimensions. So I think this is very easy to understand. We have 3 dimensions in translation and also 3 dimensions in rotation. And this is how we set up. So this is a prismatic joint, and you will move along the z I minus 1 axis. So this is joint I. So this one will be moving upward. So the Qi is equal to Di. So Di is the displacement. And if this joint is moving upward, what will be happening to the ending factor? So the ending factor will be moving in the direction of Zi minus 1, and the dot is the velocity vector. It's not it's a velocity scalar. So this is just a value, and this is the direction. Zi minus 1 direction and times Di dot. So for a prismatic joint, the linear is Zi minus 1 times Di dot. And of course, for the prismatic joint, we don't have any rotation. So the rotation is 0. Okay, I think I have a mistake here. So it's J. I'll correct it right now. So it's the joint angle I. So it's equal to 0. So do you have any problem with the translation part, the prismatic joint? So you can imagine as this joint is moving upward, and the ending factor is also moving upward in the same direction. And so the direction is Zi minus 1, and the velocity is Di dot. So here comes with the revolute joint is more complicated, but if you remember just now, dynamic angular velocity. So we know that VAB is equal to omega cross RAB. And back to here. So if we have a joint I and we have the rotation is Q theta I, and it's rotate about the Zi minus 1 axis, and what will be happening to the angle vector? So if here has a length or a link like my arm, so if you rotate, you have a translation and you also have orientation. So what is the translation? So this is from this point to this point. So this is the translation. And the rotation is m in this direction and to m in this direction. So the rotation will be this, and this is the translation distance. So you have both the translation and rotation. So if you remember the basic dynamic rotation of the rigid body, so this is the axis, rotational axis, and cross the distance, the position vector between the center of the rotation to what we want to find. So this is the position vector, and times this is the velocity. It's just a value. It's a scalar. It's not a vector. And if you rotate about the axis, then this is the rotation about the axis, and this is the angular velocity. So if you rotate in theta dot velocity for this robotic joint, and the edge vector will have a translation in this velocity and the rotation in this angular velocity. So we can separate the translation and the rotation into two parts. It's like if you have a joint. So this is the A, and if you rotate to B, so this is the translation distance, and this is the rotation distance. So we can separate the translation and rotation. So to sum up, for prismatic joints, we have Zi minus 1 axis, and for the regular joints, we have Zi minus 1 cross the position vector, and for the angular, this is 0, and this is Zi minus 1. And we will write it in this form. So this is 6 times matrix. So it will be like so for here will be translation. The gel and will be and this is the number of joints. Here will be this n is number of joints, and these are the degree of freedom. So since we have like this is x, y, z, and u, v, w. So here will be equal to Vx, Vy, Vz, and Vu omega, U omega, V, and omega R. So this is how you map the joint angle, the joint velocity to the cartesian velocity of the any vector. And so for this geometric Jacobian, so all the vectors should be expressed in the same reference frame. So for this example, is for base frame F0. So you can check, we have the base frame here. So all the axis vector is you refer to the base frame. So for the geometric Jacobian, you will only have one frame. It's not like what we did for the forward kinematics or the inverse. You have every local frame at every axis. In this geometric Jacobian, we will only have one frame. And if you are interested in this method, you can check. It has another name. It's called school theory. So it's one of my research interests. So basically, the school theory is setting up in a geometric Jacobian. And we will have a very quick example for this. So this is the two leg arm or planar two revolution arm. So here we have the first revolution joint and the second one. So this is a XY plane. And you can imagine that the rotation axis is in the Z direction. So it's as this direction. So the rotation axis Z0. So I think we can have only two. Fine. So equal to Z1, Z2. So it's 0, 0, 1. So it's in this direction. And what we have, this is the position of the A factor. So it's equal to A1 times cosine Q1 plus A2 times cosine Q1 plus Q2. So I think we already derived this in our earlier lecture for the mathematics lecture. And if you from here, we want to find the position vector of here is A2 times cosine Q1 plus Q2. So all these are in the reference frame. So how can we find a Jacobian? So the Jacobian will be Z01 cross POE and Z1 cross P1E. And here we have the rotational parts will be 0, 0, 1 and 0, 0, 1. So this is the Jacobian matrix. So from here, the Jacobian here is we have two rings. The rank is 2. So the first one and the second one. So plus we own at most two components of the linear angular velocity, any vector velocity can be independent assigned. So of course we have two joints, so we only can assign two independent velocity. So any question about the two revolution joint arm, the Jacobian? I think it's quite simple, right? And now we come to the differential kinematics, or you can say it's the analytical Jacobian. So first we'll review with the derivative. So I think most of you are very familiar with derivative of sine is cosine and cosine is minus sine. So this is the derivative formula. So we just limit the distance of the x into infinite small value, and you can have the derivative. And also we can do a partial derivative. So is you can do the first you want to do with the x and you want to then do with the y with a partial derivative. So now this is the analytical Jacobian matrix. So I think it will be more easier. It's the same concept as you learn in the forward kinematics. So the differential kinematic gives the relationship between the joint velocity and the corresponding angle factor, the linear and angular velocity. So you can see this is the linear and this is the angular. Now this mapping is described by Jacobian matrix. So this is a Jacobian, and which depends on the manipulator configuration. So it's the same concept. So this is every Jacobian depends on the current configuration. So if your configuration change, then your Jacobian change. So this is the A effective velocity, and the velocity you can separate into two parts: the translation and the rotation. And this is your forward kinematic solution. If you remember, this is a transformation matrix. It's a 4x4 matrix. And you do the derivative actually it's with t, so but you cannot derive directly with time. So we'll do a partial derivative first with the joints, and then the joint angle, then the joint angle will be doing the derivative with time. So you have q naught. So here is the Jacobian, so you can write this into a Jacobian matrix and times q. So for the one who's not really sure about the partial derivative, so this is the displacement, and it's equal to the forward kinematics if you plug in all the value. So this is the displacement, and this is the joint angle. So you do the derivative with time. So this is equal to r dot is equal to velocity. And on the right side, you will do the partial derivative with q and times q derivative by time. And this one will be equal to q dot. And this is equal to the Jacobian. So I think it's very directly. It's just derivative with by the time, so you can get the relationship between the joint angle velocity and the Cartesian A effective velocity. So as for the forward kinematics, is the relationship between the position. So you do the time derivative, then will be the relation between the velocity. So I think it's much straightforward. So again, so we can have two separate parts. So this is the position, and position in the dot shape here. So the position and dual time derivative, and you have this one, what we call JP. So it's the Jacobian for the position, and also we have the angle. So the J phi, so it's the Jacobian for the angle. But I think it's all the same. So it's just you can differentiate by yourself what you want to use. And this is the velocity, and this is the velocity in translation and velocity in rotation. And these are the Jacobian matrices. And this is the Jacobian. So how to find a Jacobian is use forward kinematic solution, or you can call it the transformation matrix. It's the pulse included the orientation and position, and derived with by the joint angle. And we will have examples for you to see. So again, this is the planar 2R. So these are the forward kinematics. I think most of you remember. So this is A1 cosine Q1 plus A2 cosine Q1 plus Q2. It's the same. So we have the Px and Py, and also from the horizontal, the phi. So directly, we can just derive it with I time. So the position, the displacement derived by time is the velocity, and cosine is minus sine, and partial derivative is Q1 dot. Then it's minus A2, and cosine is minus sine, and Q1 plus Q2, and we have Q1 dots plus Q2 dots. So we can write it. We put all the angle velocity in the matrix over here, and we can have the Jacobian matrix of these models. So it's like, so here we have Px I and Py Py naught and Y naught equal to, so and like we have the Q1 dot, Q2 dot, and Q3 dot. But we only have two. So normally, if we have three, then we need three inputs. So again, in this, we know that these are not three independent outputs. So we cannot control the x direction and control the y direction, and also control the y direction independently. So because we only have two. So by writing here, so this is minus A1 sine Q1 and times Q1 dots. And here we also have minus A2 sine, which is write in the short form. Minus A2 sine I2. And from the second one is A2 sine 1, 2. And for the y, so it's A1 sine 1 plus A2 sine 1, 2. So here will be A2 sine 1, 2. And for the y dots is Q1 dot plus Q2 dot, so it's 1, 1. So this is how you reorganize these equations into the metric form. So this is any vector velocity equal to the Jacobian, and this is the Q dot. So we come to three vertical joints. So again, we have the x, y, and y, and we have three joints. So this is the number of joints, and this is the number of degree freedom for the nth vector. So for this three after three round, the forward kinematics is solved by with three equations. So you can try to derive the Jacobian. So you can have a try. So you can follow this. So derive the px by q1 and derive px by q2 and derive px by q3 and follow this form. So you can get the analytical Jacobian solution. So after we finish for the Jacobian metrics, so it's just another derivative to the joint angles. So for px, so it's equal to a1 times cosine q1 plus a2 times cosine q1 plus q2, and this is a3 times cosine q1 plus q2 plus q3. So if you do the partial derivative by the q1, so here this is we have the q1, so it's a variable, so we have just for the sine, and here we also have the cosine to sine minus sine, and we have 132 minus sine. And for here, so since we draw by Q2, here we only have theta Q1. So this is, you can see it as a constant because this is dots. We don't have any values of Q2 inside this part, so we only have these two. And for the Q3, this is the only one. So that. And for y, it's the same, so it just changed from the sine, derivative of sine, this cosine, and all are the same. And for the angle, since it's Q1 plus Q2 plus Q3, so the derivative is 1. So we can write it as a Jacobian matrix. So it's the Jacobian will be looking at this. So if you times the angle velocity over here, then the output will be the n effective velocity. And when it comes into mobility analysis, so if Jacobian has a max rank, so typically you can call it n in the configuration Q, then the robot n vector can move in any direction in the task space, in the n space. So it's like if you have the max rank is 2, then you can move in 2 directions, different orthogonal directions. And typically, if you see for our 6 revolution joints industrial robots, then the rank is 6. So you can move in 6 independent directions, the 3 translation and the 3 rotation. And since that the Jacobian matrix change when in different configurations, so there are some configurations that the rank of the Jacobian is less than what you expected. Then there exists the direction of in Rn alone, which the robot anyway cannot move. So it's only instantaneously at this configuration. So if your rank is not 4, then there will be some direction that your robot cannot move. So in this circumstances, we call this the kinematic singularities. So the singularity is defined as the configurations where the Jacobian loses rank. So that will affect the robots cannot move in some direction. So it results loss of instantaneous mobility of the robot's n effector. So for m equal to n, they correspond to Cartesian forces at which the number of solutions of the inverse kinematic problem differs from the generic case. So you can see if you are in a singular configuration, then we cannot find a joint velocity that relates a desired n effector velocity in a arbitrary direction of the task space. So I know the explanation may be quite difficult to understand, but you can just imagine that so this is our Jacobian, and this is our joint angle velocity. And we have like a lot of Jacobian, and we have all these end joints. And if this full ring, it means that all these, all the numbers in these vectors have value. But if it's loose ring, this means that if you just calculate the vectors, then you can find 1 is 0, 0, 0, 0. Because if you lose ring, that means that 2 of the column are the same. So you can change one column into all 0. Then, so I think I remember. Okay. So that's when one of your joint, like if it's the last one, then the joint end, you cannot determine what will affect to the can like say it in the other way from here. So if you are loose ring in the rows, then there will be one direction you cannot really control because you have all the 0 in that row or column. So if you see some motion in the industrial robots, if it's close to a singular point or close to a singularity, then large joint velocity may be needed to some very small velocity of any vector. So it's like if you're close to a singularity point, then maybe if you want to move a little bit, then your robot will be moving a lot and just want to pass or get through that area. So if you see like a very strange motion of the robots, then there might be a singularity point nearby. So what we want to do is we want to avoid these singularity points when we plan our trajectory of the robots. So we don't want the robot to move like this very large motion. So finding analysis in advance, all singularities of the robots helps in avoiding them during trajectory planning and motion control. So if you have a Jacobian, then you can, if the n is equal to n, so if this is the mobility equal to the number of joints, it's like if you have 6 joints, like our 6R robot arm, and it's moved in 6 degree of freedom, then it's 6 equal to 6 for the spatial case. So find the configuration, that's the determinants of the Jacobian equal to 0. So if the determinant equal to 0, that means that in this configuration, the robot is in singularity configuration. And sometimes we will have like the joint angle is larger, the number of the joint angle is larger than the mobility. Then we can find all the n times n minus of the Jacobian, and we also find its this Jacobian determinant, this one, n times transform equal to 0. Or you can just find this one, the determinant is equal to 0. And so finding this all the configuration may be a very hard computational task. Although we have this question for in your homework, but I'm still thinking whether you need to find all the configuration or you can just like provide 1 or 2 configuration, then it's fine. Okay, so we'll have a break. So if you have any question about the Jacobian, then you can come upstairs. Okay, so we'll continue with our singularity analysis. So again, this is familiar to our arm, the final arm. So this is the Jacobian. So we have just derived the Jacobian of these robots. And if you calculate the determinants, then you can see it's A1 times A2 times sine Q2. So when will this Jacobian lose rank? Is when the determinant is equal to 0. Then this matrix will lose rank. So A1 is a constant, and A2 is a constant, and the only one will be the Q2, the sine Q2. So if we want this determinant is equal to 0, then the sine Q2 is equal to 0. So what are the singularity condition? Is when the Q2 is 0 or the Q2 is equal to pi. So what will be like for the Q2? So for Q2 equal to 0, so this is Q2 equal to 0. And what will be like Q2 is equal to pi. So it's backward. So in this configuration, Q2 equal to pi. So for this robot, there are only two singularity configurations. The first one is Q2 equal to 0, and the second one is Q2 equal to pi. So I think because this is a very simple robot, so it's very easy to find the singularity configuration. And when we do our trajectory planning, and we need to avoid these two configurations. So if you in the future, if you do like control or the trajectory planning, then you need to avoid when the Q2 is near 0 or near pi. So the singular configuration corresponds here to containment points on the boundary of the workspace. So we can easily draw this workspace. So it is maybe even this is the largest part, and when it's go back, so for this robot, these are the workspace. The robots. So here it's touching the boundary of the workspace. So in many cases, these singularities pervert regions in joint space with distinct inverse schematic solution. So like we can have like elbow up or elbow down. So between them, they will have a singularity. And now we can see this is the polar arm. It is in the three-dimensional space. So we have px, py, and pz. And this distance is d1, and this is a vertical joint, and q1, and a vertical joint in this direction, q2, and this is a prismatic joint for q2. So for forward kinematics, px is equal to q3, this is the distance or the length, times cosine q2, and times cosine. This is cosine q2, and this is maybe here. So here will be the cosine q1. So it's px. Then for py, it's the same. Cosine q2, and then project on the xy plane is this distance, and this is the sine. And for the PZ will be d1 plus q3 times sine q2. So these are the forward kinematics solution. And through the derivative by the angles, this is by q1, q2, and q3. Then you can have the Jacobian matrix. And if you calculate the determinant of this matrix, you can get is equal to q3 squared times cosine q2. So if we want to find the singularity position of this robot, then we can set determinants q. The determinant of the Jacobian is equal to 0, and you can find there are two solutions. One will be cosine q2 equal to 0, the other one is q3 equal to 0. So for the first one, the A vector along the z-axis, q2, when q2 equal to, here have a divide. So when q2 equal to plus or minus 90 degrees, then this will be 0. So the determinant is 0. So the rank of the Jacobian will drop. So you can call it a singularity. So the rank of the Jacobian is equal to 2. That also means that it loses one direction. So if at the same time, the Q3 is 0, you can see if it's 0, it means that Q3 is also in this point. So they have double singularity, so the rank will be dropped to 1. Because that you cannot control the position since that it's all at this point. So all singular configuration corresponds here to consistent points internal to the workspace. So it's inside the workspace. So this is how you find the singular configuration of the robots. And there are also other methods, but this is the typical one. You just calculate the determinant of the Jacobian equal to 0. And now we come to the differential inverse kinematics. So last week we talked about the analytical inverse kinematics, and if you want to solve the analytical inverse kinematics, you need to, I would say by luck. If the robot is very difficult, or maybe you can solve it by some software, or you can just you need to do the inspection by yourself, and you just calculate all the angles and find all the angles solution. And now we will introduce differential inverse kinematic, and this is a numerical method. So it's different from the last week. So a highly nonlinear relationship between the joint space variable and the orientation space variable causes known solution or redundant or closed form solution for inverse kinematic. So this is called the analytical kinematic. So a linear mapping between the joint velocity space and the operational velocity space in differential kinematic equation tackles inverse kinematic problems. So the differential kinematic is this is the velocity of the impact vector, and this is the translation rotation, and this is the Jacobian times the angle velocity. I think maybe you familiar with this because we will all talk about this formula or this relationship. in this lecture. So if we want to find the Q dot, then we can times the inverse. This is the Jacobian inverse. And we can form the formula into this form. So the desired jump velocity depends on the desired position and the orientation of the end effector. So it can be obtained via simple inversion of the Jacobian matrix. So you just times the inverse Jacobian to both sides, and you can get this one. So there are some prior to this calculation, the Jacobian must be invertible. So Jacobian is a square matrix, and the determinant is not equal to 0. And also, although this is, theoretical, it needs to be a square. But if you you can use something like the pseudo inverse. So it is an approximation to the inverse when your Jacobian is not a square matrix. You can also obtain the inverse matrix of the n times n rectangular matrix. You can use a pseudo inverse. So in MATLAB, this is the function. The INV inverse is called inverse, and brackets A, then provide the inverse of the n matrix. And you can also look up for the pseudo inverse if you have encounter n times n. So this is what we get from the last formula. Then for a very small interval of time t, then Q dot and V can be assumed as a constant. So I think these are very similar method to a lot of physics classes. And so Q dot times t, this is the velocity times time, then it's equal to distance. So this is the angular distance, and this is the Cartesian displacement. And the relationship between the angular displacement and the n effector displacement is inverse of the Jacobian. So this is the main concept of the numerical method for the inverse kinematics. So that's the displacements in the joint angle, and this is the displacement of the n effector. And the relationship between them is the inverse Jacobian. So this is the main concept of the numerical inverse solution. So do you have any question about this one? So we will have an example to show you. So suppose that in this configuration, you can call this E over n effector. So this poles, this have px, py, and phi, and it's at the n effector as this current configuration. And what we want to go is this configuration for these poles, is pxd and pyd and phi d. So this is an inverse kinematic problem. We need to find, we have the poles, and we need to find the joint angles. So this is an inverse kinematic problem. And how we can solve this through the numerical method. And also this is, you can say the delta R is equal to the displacement between them. So it's equal to RD minus RD. And if we have this formula, we just derive then this is the displacement of the angle, and this is the Jacobian inverse, and this is the displacement of these 2 points, and it's something like this. So we can just have this transpose. This is the Jacobian transpose. The inverse. So it's the Jacobian and inverse. And here is the displacement of the n effector. So we know that this is the first position, and this is the position, the pose we want to go. So we just have the displacement between them, then times this one, then it will equal to the joint displacement. But this only happens in instantaneous, or you can call a very, very, very small amount of time. So it's called instantaneous. So this means that if you have like a displacement, then then your answer will be close to a real value. It's not a real value. It's not a true value. It's just an approximate value. So by this, you can just times the Jacobian transpose, and you can map your change of the tool position to change of the angle. So this is the main concept of the numerical inverse. I think it's much simpler than what you have done in your homework, right? So this is from the forward kinematics, and you just do the Jacobian, just forward kinematics, then do the time derivative, then inverse, then this is the relationship between the inverse kinematics. So this is the current or the joint space. So the joint space after adjustment is the Q adjust is equal to the delta Q plus the Q current. So it's iteration like in last week, if we want to find this configuration, and what we have is this. This is the 0 configuration, or you can call it the initial configuration. So this is this configuration when you set up your coordinate space, and this is what we want to find. So we give you the poles of this is px, py, and phi. I think last week the homework, the analytical is you need to solve it by the geometric problems. So if this is given, then you can just calculate the. You really don't need this one. So you only need to set up your coordinate space. Then you can, if this is given, and through the analytical inverse kinematic, then you can get theta 1 and theta 2 and theta 3. 1, 2, 3. So I think you still remember what you derived during the homework or the 2 weeks before. It's like the pose is given, then you will, through the inverse kinematic, you can calculate all the vector angle. But in the numerical method, you need to have the initial So in the analytical, this one is not needed. If you have already set up your coordinate space, you do not need this initial configuration. It's only needed to set up the coordinate space. Then afterwards, if you have the inverse kinematic, you can solve it directly to this operation. So this is for the analytical inverse. So if you give you a pulse, then you have your inverse kinematics, and you can get the 3 data interval. But in the numerical method, if we want to solve this one, then what we need to do is that we can calculate that this is the displacement, and if we can just, because if you want very accurate, then you cannot go very far. Maybe you can just, you need to just go like very, very tiny distance, very, very tiny. So the second one will be something like, maybe it's not like this one, because it's very tiny, so it's almost the same. And go to here, and then just another step of very tiny, then go to here. And a lot of like depends on your accuracy, and this is just go very, very tiny distance and to the point. So you need to do a lot of iteration. And every time when you have the delta R, this is delta R, then you will get delta Q. So maybe you can call this delta R1 and this delta Q1, and this is delta R2, and here we have delta Q2. So like you have many kinds of iterations. When you get to your final destination, then you will add the delta Q is equal to delta Q1 plus sum up and Qn. Then this is your angle displacement. So unlike in the analytical, you can just directly calculate the absolute value. In the numerical method, you will only calculate the relative value. So you need to have a Q0 and you plus the Q, the delta Q. Then you can get, this is your answer. So you need to have an initial configuration, the Q0, and plus the delta Q. And by the analytical, you can directly find the Q. You do not need the initial configuration. Because in numerical method, you calculate the relatively angle levels. So we also have an example for this. So it's like a given joint input is Q1, Q2, Q3. It's 0 to pi. And the increment for these three is 0.0157 radians. So these are the steps, and these are the radian. So it's from 0 to pi, and we divide it by 200 steps. So we have 200, it will move 200 steps before we reach our destination. So this is all the same. So if you want to find the 200 step, actually if you want to find the analytical inverse, you can just directly, if you want to find this point, then you can just directly calculate it. You don't need all this iteration. You can just find the answer. You can just find this answer if you're doing the analytical. But if you're using differential inverse, then this is what you need to do. Is you need to do the 200 steps before you can sum up all the delta Q. And plus the initial, maybe the initial is 0, 0, 0, and plus all the delta Q, then you know what is the Q for this configuration. So if you see for the differential method, always have a lot of noise. This is the input. And if you see the analytical, then it's just a straight line. It's almost the same because this is analytical. And if you see the error, this is 10 minus 3 dimension. So they have very large errors. And if you see the analytical, it's 10 minus 15. So this noise is basically the computation of digits. In theoretical, you can get the true value, even no errors. So differential inverse schematic results have you can call it small error, or you can have has error. Then error compensation method could be applied. For the analytical inverse, then if your number of digits is calculated very large, then this should have even no errors. The errors is because of like the digits limitations by the calculation. Maybe I'll change it. Not using small. So the differential inverse result has error, and this error depends on how many iterations, how many steps you take, and that is because that like for instance, if this is one configuration, and you know that your velocity is going in this direction, and so the Jacobian you use, the J transpose, the Jacobian inverse you use is for this configuration. So this is the velocity you calculate, and this is the instantaneous velocity. But we have a displacement. So if like the second one is moving to this direction, then we assume that in this interval, all the velocity is traveling in this direction. So that's why it has an error, produced the error. So in this interval, from A to B, the velocity is a constant, but in reality, velocity should be changing when your robot is moving. But through this numerical method, the velocity we assume as a constant because we didn't change. As we have stated that the Jacobian matrix will change when the robot's moving. So when the robot has different configuration, then the Jacobian will change. But we let it go like delta R or delta T because we need to travel it. So during this interval, we only use we use the same Jacobian. So like if we in the middle, if we have this configuration, then we use this one should theoretically should have like J2 Jacobian, but we still use the J1 Jacobian to calculate here, because we only use one Jacobian throughout this interval. But in reality, the Jacobian will change. Yeah. So this is why numerical is called an assumption. You will have produced an error. Because we cannot have like every moment that we have all the instantaneous Jacobian. So this is a typical loop for if you want to travel RD to RD, then this is your position right now. So if you minus it, then you can produce the error. And the error is the distance you need to move forward. So like this is the error, and this is the Jacobian of the current configuration, then times the Q naught. Then you do the delta. This is the interval. Then plus the initial configuration. Then you can get your final. So this is the Q here, and the Q0 is here, and this is if you times the Q naught, then this produces the delta Q. So here, then through the Bohr kinematics, then you can have your new R, and you compare with your destination. Then you just minus it. Then you have your error. Then this is a closed loop. So you have a target. Maybe the E is smaller than your threshold. Then you can have your Q. So this is the complete numerical inverse kinematics method. And how to minimize the error? There are a lot of methods, different methods. So one will be like you can use this one. And this is when it's smaller than 0 and you reach the stability. And you can look up, they have a lot of methods to do dealing with the stabilities of the inverse kinematic. So to sum up, the analytical inverse kinematic, the advantage is the absolute ineffective pulse. So just how we have already said that if you have the configuration, you have the pulse, you have the inverse kinematic, you can directly calculate or derive all the angles. And theoretically has no error. Just now if you see any errors, that is because of our computational limitation. So theoretically they will have no errors. And the disadvantage will be difficult to derive. I think you have, if you do your homework, I think you know it's very difficult to derive. And that is a very commercial and very common robot, a 6 bevel joints, and there are a lot of very complicated robots. So the analytical inverse kinematic is very, very difficult too. And it is, if you have different model, then the method to derive the inverse kinematic is different. So you don't have a general solution for that, although there are some papers present have general solution, but all are not very valuable to use. So another one is you have multiple solutions. It's like in practical, if you use the analytical solution, then you have like 8 solutions simultaneously. So you need to choose which one you you want to use. So normally you'll choose that the solution that is the joint angle is relatively near your current joint angle. You will choose that solution because you don't want one of the joints rotate a lot of angle to have that destination. And for the Jacobian inverse kinematic, the advantage is that this has a systematic way to derive from the forward kinematic equation. So as forward kinematics equation is much easier in serial robots, so you can just derive it. And we also have the DH method. It's very fast to generate the forward kinematic solution, and you can just do the time derivative, then do the inverse, then you can have your Jacobian inverse kinematics. So there are ways to automatically handle the multiple solutions, because when you do this, you only have one solution. So that's how you can handle multiple solutions. And the disadvantage is it is the incremental and effective pulse. So only works when the increments are relatively small, or if you didn't use this relatively small, you can just do a lot of iteration, so you'll correct back to the stable condition. There are two ways. The first one is you increment very, very, very small. Then the second one is you can do a large, but you need to stabilize by iterations. So the control theory is up here. You just keep on checking the error and finally it will stabilize to your destination. And theoretically have error due to the approximation. So this is because we approximate that the Jacobian during the intervals is equal to the initial Jacobian. And this is just for the next, and we'll just quickly go through some control system and motion control. So this is typical robot control system. This is design with behavior. This means your desired configuration, and you'll go into a controller. Then the controller will produce the low power controls and go into the amplifier. And the amplifier will have the high power controls, sending the currents to the actuator and transmissions. So basically, it's like you sending the high power current into the motors. Then the motors will generate force and torques, and then you have the motion of the arm. So the motion of the arm will be, and the force will come back to the sensors, and the sensors will send it to the controller, and you will have the error. And do it again. So this is the loop. And if you see here have a local feedback, so the local feedback will be the control strategy of the actuators. So these are the control strategy of the robots, and this will be a control strategy of the motors or the actuator. So this is the error dynamics. So if a design point is theta d, and we can say that the joint error could be defined as this is the joint error, and this is the desired position. Desired minus the current one. So this is the error. Then usually it is, you can see it's you have how it's going to its settling the steady states. And this is your steady state errors. If you like inside this, then you can count it as Alright, so for the feedforward control, I think it's very simple. You just don't care where it's going, and if like you just go in that direction, then you just set it velocity. So usually in robotics, we will have the feedback control. So it is a closed loop. So like this is a P controller. So P controller will have a KP. So this is the desired minus the current. Then we have the KP times the error. And then this is the PI. So we all have the KP and plus this is the integration. And also we can combine the feed forward and feedback, and you can have this combined together. And I think that is for today's lecture. So do you have any problem with the derivative kinematic? Differential kinematic. So any questions? So our exam will only have the analytical Jacobian. We will not have any questions about or the problems about the geometric Jacobian, because this is our system. So we'll stick on the analytical. But if you are majoring in robotics and you're interested in school theory, then you can look up for the geometric Jacobian. So because sometimes if you are doing the parallel robots, the parallel robot is different from the serial robots. The serial robots, the forward kinematic is very easy to derive. I think you all have already know. But in the parallel robots, the forward kinematics is much more complex than the reverse. So for the parallel robots, sometimes the geometric Jacobian will be easier to find because your forward kinematics with solution is difficult to find. Like this is because that currently, if you like doing the serial robots, then every joint is an actuator. So you can just set the body frame, and here has all the angles, and these are all actuated. But it's different when you're doing the parallel robot version. So like for this is the 5-bar linkage. So the 5-bar linkage parallel robot, this is a fixed ground, and this will be actuated 1, and this will be actuated 2. And all these 3 will be passive. So how you solve this, how you find the position of here, because this is passive, you cannot input the angle of that. Then so you need to solve this constraint. You have this vector loop and here vector loop, and you have constraint that you find these 2 angles and finally find this. So for the parallel robots, the forward kinematic is much harder. So that's why the geometric Jacobian is easier to apply on the parallel robots. But since that in this course or this module, we only handling the serial robots, so the analytical Jacobian is enough, or it can solve all our questions about the Jacobian. So any questions? Then I will introduce the homework. So this is the last homework. So the first two questions I think is just explain the definitions. So it's simple. You can find it in the lecture notes. And question one is derive the Jacobian matrix of the finite robots. So depends on, you can use the homework 2 solution or you can use your own solutions. It's fine. Yeah. And then identify the singular configuration of the robots. So I'm not thinking maybe identify how many configuration need to find all. Maybe quite difficult. So maybe like I'll add a number. You can just like find maybe 2. But 2 is very easy. You have one thread and another bit. So yeah. So maybe you need to find more. So and then you need to. So the question 3 is that given that the initial and the final pulses like this. So this is also from your homework 2 as remember. So in the last homework you done it through the analytical inverse method, and in this we will do the numerical. So here we have defined that the delta R is R1 minus R0 and divided by 4, so you have 4 steps. So that might be very, very big errors inside this. And we assume that all the angular velocity and any vector velocity can be assumed by constant during the intervals. And this is why it has the errors conflict. So if your any vector coordinate system is different from the homework 2 solution, then you may use your own settings. And you need to adjust the transformation matrix accordingly from the initial and final pulses from your homework 2. And the last question is present the error analysis of the IELTS and question 3, the answer to question 3. You need to present an error analysis. So the error analysis is, you can present it very simple. It's like after 4 delta R, then you'll get transformation matrix of poles and plus delta of the angles. So just you have the desired, so you can just the desired poles and minus that. Then this is the error. And if you check the homework 2, you have the desired U and just minus it. Then this is the error. So it's really simple. And I think that's it for the homework. So any question about the homework? Or do you think it's too difficult? But I think you are very familiar with the finite robot, right? You have already done it like from the position analysis, velocity, and now, but we didn't do the statics. Yeah. And you do all the 2 kinds of methods for inverse. Okay, so maybe we will have a break. And if your group are presenting the case study, today, then you may come out and upload your files to it.
Today we are going to present the robotic case study and robotics. So first, let me make a brief introduction for our outline today. So we're going to introduce the brief concept of aerial robotics, and next we are going to break down the structural analysis for the aerial robotics, and we will finalize with the applications and exploitation. So, what is aerial robotics? So, aerial robotics is known as a drone or unmanned aerial vehicles (UAV). So, it is designed to operate autonomously or semi-autonomously to make a flexible three-dimensional aerial movement. So, what's the difference between the aerial robot and normal landing robot? Is the flying ability for the aerial robot. So when we use the aerial robot, it will provide us the 3D dimensional expansion or navigation or even mapping. So that's the application we're going to talk about next. And as for the structural of the aerial robots, we divide it into 7 main components: the front body, power source, flight controller, control system, propulsion system, sensors, and communication system. And I will going to talk each of the components one by one. So the first, the most important one is the front body and the power source. So the front body supports all the structure, every sensor's components on the drone. So you will need a high load bearing ability and the flight stability. So usually we will use the lightweight but strong materials like carbon fiber, aluminum alloy. And the next one, once we have a structure of the robot, we need to make it move. So that's why we're talking about the power source. And usually we will use different polymer or different ion battery for the drone power source. And in some industrial using, we will also use the film system to make their power source. And next, when we have a model of drone, we need to control it. So there are two systems, the flight controller and the control system comes up. So the flight controller is the brain of the aerial robot. It processes sensor data to ensure the flight stability. And also it can adjust the motor to make the navigation or some flying control. And next is the control system. So control system usually can take in two operations. So the manual control and the autonomous control. The manual control is easy to understand. So it's the operator use the ground station or some remote controller to talk with the flying drone and send the real-time mission to make the control do their task. And the other way is the autonomous control. It will be pre-programmed some flying task or some flying destination to make some specific task. And the last three parts of the flying drone is which make them different. So there are three parts that the propulsion system, sensors, and the communication system. So the propulsion system is based on your propeller's design. So this design will influence your flying ability to provide a flight thrust and make your flight more stable. And the sensor is applied to many different missions of the drone, such as GPS to make some navigation, LiDAR to dictate the length or do some 3D modeling, and the cameras we use for the image processing, and the IMU is to detect the flying acceleration and the angular velocity to adjust the flying stability. And the last one is the communication system. Usually we will use radio wave Wi-Fi to make the real-time transmission to make different data training. So before we jump into the application part, I want to summarize about the structure of the drone. So we mentioned the frame, body parts, power source, flight controller, control system, propulsion system, sensors, and the communication system. And next we will go to talk about the application of the drone.
Good afternoon, everyone. Following the introduction, let's now explore the various ways in which aerial robotics are being applied across different electricity applications. Here are the 6 applications. Agriculture and construction and infrastructure inspection, and in particular surveillance and security. Drones are now essential tools for enhancing security operation. They are then equipped with cameras and real-time data feeds, allow them to efficiently monitor virtual areas. This is especially useful for city policing, where drones can record real-time video to help officers respond faster to incidents. Drones are also used in broad security to control difficult to reach area, providing better coverage and reducing the need for ground patrols. And here is logistics and deliver and think and photograph and actual logic. In particular are logistics and deliver. In logistics, drones are transform the delivery process. Companies like Amazon use drones to quickly deliver packages, especially in urban areas where traffic can be a problem. Drones can bypass this by flying over compressed roads, significantly reducing delivery times. They are also great for delivering small packages to remote or hard to reach area, making logistics for eventual overall. Classification. More on the classification of aerial robots. Drones can be grouped in different ways by the most common classification based on their design and usage. By design, rotorcraft also multi-rotor drone. This drone have multiple rotors and are highly maneuverable. They are ideal for short-range operation like deliveries and inspection. Fixed wheel. These drones resemble airplane and are designed for long distance flights. They are perfect for tasks like mapping and surveillance over range area. However, there's combine the ability of both rotorcraft and fixed-wing drone, although for vertical takeoff and long-range flights. By usage, counting drone, these are used for tasks such as industry or inspections, agriculture, and logistics. They are equipped with precision sensors and are capable for autonomous operation. The miniature drones primarily used for reconnaissance and combat missions. Military drones feature advanced control and real-time data recreational drones. They are designed for personal use, often in photography or reaching. They are simple to operate and feature-based inspection. Aerial smart is rich in gestures such as surveillance and logistics with diverse design and cutting-edge technology. Drones can be custom to meet special needs, making them an essential for today and in the future. And here is our reference. Thank you.
So, any questions for the aerial robots? Okay, so I have a question. So, you have introduced like a lot of drones, and they have different number of rotors. So, why the drones have different number of rotors? And the second question is, why most of the commercial drones choose 4 rotors?
So for the first question, why do we use why are those from usually use 6 motors? We think it's for different usage. So like some, I think we think maybe you need to carry more heavier package or need more stable flight control, so you will need 6 motors. So usually for the cost saving perspective, I think the 4 motor is more useful, more common, and can adapt it to more public mission like photographing or searching for some Yeah, so we think ball motor is more useful for some searching issue.
So can the drone use 3 rotors?
I think he can keep, but it's okay, I think.
So using 1 rotor cannot balance?
Using one, maybe it's like,
What do you mean, like helicopter?
Yeah, so Android helicopter have 3. So, maybe it's something like that. Thank you.
Thank you. Okay, good afternoon everyone, and we are two. Today we are going to present our topic, parallel manipulator. And so first, we want to introduce the definition and the characteristic of the parallel manipulator, and then we'll go through the structure analysis and the classification, and finally the application in the real world. So, what is the parallel manipulator? We found explained in the book called Parallel Robot Second Edition. It's written by David Merlin, and the book said a generalized parallel manipulator is a closed-loop kinematic chain mechanism whose an effector is independent to based by several independent kinematic chains. So just like the figure shows here, it's a closed-loop kinematic chains, and then each link is independent to each other. And then, because it's a closed-loop chain, so we think it can distribute the load by its links. So it has a higher load carrying capacity, and then because this structure can make the manipulator move faster and then more accuracy. And then in the book we already mentioned here, the book say that there has been shown for the 3 degree freedom per robot that the average energy usage is 26% of a zero manipulator of similar size. So we think this will have a lower power usage compared with the similar size serial robot.
In this section, we will explain how the parallel manipulator operates structurally. Upon initialization at the start of operation, the system first processes incoming signals, which can come from sources such as cameras, pitch pendants, or computer components. The processes signals are then used as input components for the operators. Following task planning, forward and inverse kinematic calculations. The system checks for simulator keys before building the end effector to the target point. In this section, my partner and I will individually introduce two types of parallel manipulators. The first is parallel robot and the other one is steward platform. First, parallel robot. The reason why it's named parallel robot is said to come from its resemblance to the three-plater robot. And in addition to the general features of parallel manipulators mentioned earlier, the parallel robot has three-arm structure and is typically used for test kits that require high repeatability and efficiency. And now let's talk about some applications of parallel robot. I will give two examples. First is parallel pivoting for robot, and the other one is recycling robot. And this is one of the most famous projects involving table times robot in recent years, and it developed by Homeworld. This robot uses 3D cameras to track the position of the ping pong ball and human players' motion. It then calculates the trajectory of the ball and selects the optimal hitting pattern. It's showcasing a great example of interaction between humans and robots. And the second example is a recycling robot. Due to increasing labor expenses and workforce scarcity, recycling robots have become an excellent substitute for humans working in dirty environments. This robot helps reduce the risk of infections for humans who will otherwise be exposed to sanitary competence for prolonged periods. Additionally, they solve labor issues and significantly improve work efficiency.
And then I want to introduce the second classification, the steward platform. And like the picture here, you can see it has the 6 prismatic actuator, and this actuator normally uses the hydraulic and or the electric actuator. And the steward platform has 12 connection and 6 on the top right and 6 below. And the connection here is usually is a rotor joint, and we can provide the rotary motion for the and because the 6 scroll freedom sometimes it codes 6 axis platform, and also you can call it 6 scroll freedom platform. Where is the steward platform used? It's usually used in the motion simulation or the environment simulation. And the first case is the MIPA. It's a telescope used in the astronomical field, and it's steward platform is used in the base. Used as the base of this telescope, and then the second case is the motion simulation, and it used as the flight simulator or the earthquake simulation, and also the base. And the third case is the hexapod MAST, and usually used to do the vibration test to check whether the electric component is performance during the vibration. And this is our presentation. Thank you.
So any question for the parallel robots? Okay, I'll just have a simple question. So can you just name a few advantages of the parallel robots and also the disadvantage of the parallel robots compared with the serial robots?
I think it's the high load capacity and the fast and more accuracy. The high load capacity is because the load distribution will provide the link independently, and compared to the serial robot, it's directly the link is linked to each other, so it has information, something like that, I think. And then because it has more higher stiffness, so because it has a higher stiffness than the parallel robot, so I think it will provide more fast and precise positioning in the process compared to the serial robot.
What about the disadvantage?
I think it's workspace. The parallel robot is limited in the workspace, and the serial robot its workspace depends on the link to each one. So workspace.
Okay. Thank you.
Hello everyone, my name is Zhang and he's my partner Zhang Yongxie. And today we are talking about our case study, serial manipulation. And this is our outline. So what is serial manipulation? It's a type of robotic arm consisting of a series of interconnected links and joints that work together to move an effector through the space. This configuration allows for greater flexibility and reaching manipulating objects.
making it a popular choice in automation and manufacturing process. It can perform complex tasks due to their articulated structure, which enables them to achieve a wide range of motion. And this is a structure of a serial manipulator, and we divided it into five types. The base is a part of a robotic arm that is fixed, usually anchored to the ground or a workstation. It provides stability to the manipulator and often contains the first joint. Joints are the moving parts of the robotics arm, each providing a degree of freedom, typically in the form of rotation or translation. Common robotics arms have 6 degrees of freedom. These are the ridge structures connecting nearby joints. The length and shape of each link define the working range and size of the manipulator. These allow relative motion between each part of the joint. The end effector is located at the end of a robotic arm. It can be a gripper, breaking gun, or suction cup, or other tool. It performs specific tasks such as grabbing objects or performing machine operation. And the final type is the control system. It's the brain of the robotic arm, calculating the sensory to control the movement of the joints, ensuring position of the end effector. Common control methods include forward dynamic or inverse dynamics or real-time pace adjustment using sensors. And here are the figures about 3 types of manipulators. From left to right are serial, on-site serial, and parallel. The table is showing the difference between these 3 types of manipulators. About serial, it forms an open chain structure composed of a single sequence of things connected by joints, with highly flexible with a large range of motion. Is suitable for tasks requiring wide reach. However, errors accumulate across joints, leading to lower precision. Also, it has poor load capacity. About quasi serial, it performs a hybrid structure with combined serial and parallel elements. It's more stable than serial manipulators, with improved load capacity and precision. It retains some flexibility, so that it's a good choice for tasks requiring a balance of rigidity and precision. About parallel, it features a closed-loop structure with multiple links supporting the end effector. It has extremely rich and precision with excellent load capacity, but the range of the motion is more limited. Also, it complex to control due to its multi-link system, but it provides a highest precision and stability. And next part, I'll talk about the history of serial manipulator. In 1954, George Stable invented the Unimate, the world's first industrial robot and serial manipulator. It used NC technology and could handle text based on pre-programming text. Unimate was the first used in the automotive industry and four-way. In 1961, Unimate was officially introduced by an automation company and used in General Motors factory. It marked the beginning of serial manipulators in industries. From 1916 to 1980 was the rapid development of the serial manipulators. There are some important cases during this period. Rachel was developed at Rachel Ross Clinical Hospital in California in 1962. It was one of the first robotics designed specifically for people with physical disability, and this is known to be the first robotic arm to be fully operated by a computer. And next, the Minsky-Burnett arm was developed in 1968 by Marvin Minsky and Bill Burnett. It was an advanced robotics arm designed for underwater use. The arm was famous for its human-like flexibility and dexterity. And next is the Stanford arm. It was developed in 1969 by Victor Chamber at Stanford University. It was one of the first robotic arms to feature this degree of freedom, allowing it to replicate the range of motion of a human arm. The arm was controlled by digital computer, making a major breakthrough in robotics automation. It becomes a foundational design for future industrial robots. And next, in 1973, Kuka developed the first industrial robot powered entirely by electric motors. This innovation made a huge change for hydraulic systems that commonly used in that time. Kuka's robot was called famous and became one of the earliest electric-powered robots, setting a new standard in precision and control for industrial application. And then is Silver arm. It was designed by David Silver and MIT in 1974, which did a small part assembly by using feedback from delicate touch and pressure sensors. The arm's movement approximates those of human fingers. During the same year, this arm led to Victor Sherman, the inventor of the standard form, to manufacture industrial robots. Sherman was instrumental in the creation of the Puma for innovation company. So Puma was created for General Motors and became one of the most widely used industrial robots. Its design was inspired by the 6-degree freedom of a human arm, allowing it to perform complex tasks such as assembling, welding, and material handling. In the 1980s, mathematical modeling of serial manipulators was started, such as robotic dynamic or Jacobian matrix or rigid body transformations become common, forming the foundation for robot motion control. More industries, for example, electrics or food processing, began using serial manipulators during this time. In 1990s, with the rise of AI and sensor technology, serial manipulators become more autonomous and flexible. Robots with multiple degrees of freedom and sensors could handle complex tasks. Modern serial manipulators are highly flexible and be used in fields like medicine, service, space exploration, and precision assembly. For example, the picture is the UR series robots, and it is lightweight and flexible and programmable.
And I will talk about the applications of serial manipulators These robotic arms are used in various industries due to their flexible and precision. One of the main applications in manufacturing and automation where we commonly see them in automobile factories. They handle tasks like assembly, welding, and material handling. In the medical field, serious manipulators can even be used in surgeries, such as the well-known Da Vinci surgery system. It allows surgeons to perform minimally invasive procedures with high precision and control through the robotic arm. In space exploration, serial manipulators are used in space missions for satellite maintenance and sample collections. These robots perform tasks in extreme environments where human invention is not possible. They are also used in research and development, where they handle hazardous materials with precision or conduct experiments that require receptive and accurate movements. Next, I will explain the classification of serial manipulators. There are many ways to classify them, but I will focus on the four most common methods, which are based on degrees of freedom, kinetic structures, applications, and control strategies. First, they can be classified by their degree of freedom. A 3DLF manipulator is suitable for simple tasks like pick and place operations, while a 6 degree of freedom manipulators can replicate the full range of motion of a human arm, making it ideal for more complex assembly tasks. Manipulators with 7 or more degrees of freedom provide randomness, which allows them to avoid obstacles or compensate if one joint fails. Next, serial manipulators are classified by their kinetic structures into 4 types. First, the Cartesian manipulators, which use prismatic joints for linear movements, commonly in CNC machines. Then, the cylindrical manipulators combining prismatic and rotary joints to create a cylindrical workspace, ideal for assembly and material handling. Next is the Scara, combining rotary and prismatic joints for precise pick and place tasks, especially in horizontal movements. Finally, the articulated manipulators, resembling a human arm with rotary joints, used in industries for tasks like welding and plating. And by applications, industrial manipulators handles heavy tasks like welding and assembly in industries such as automobile and electronics. Many medical manipulators are used in surgeries, enable precise, minimally invasive procedures like those performed by the Da Vinci robots. Cobots work alongside humans, assisting with tasks like assembly and testing, especially in shared workspace where safety and physical are key. And based on the control strategy, we have 2 main types. First, position control manipulators, which focus on precise position of the end effector. These are commonly used in tasks like assembly where accuracy is critical. Then, we have force control manipulators, which emphasize controlling the force applied by the end effector. This is important in tasks like collision or grounding, where maintaining consistent pressure is key. And here are our reference.
Thank you.
So any question for the serial manipulator? So I think that your group are very lucky because we have like at least 2 months. We will just keep on studying the serial manipulator. So I think you are very familiar with that. So based on your presentation, I'll have 2 questions. Can you go to the control theory classification slides? Yeah, so based on the control strategies, can you briefly explain how these 2 kinds of control strategies control the robots? So what are the sensors or what are the control strategies they use, and what is the sensing physical parameters to control this kind of robots?
I think the position control is you have to the way the robots go is we have set the position like that, and by the force control that maybe it touch something, and the force control can find out which end here is something and he push it, but the control and position control that he can that the arm cannot think that it hit something and go right away like that.
So because as we have already studied more deep into the serial manipulator, so can you explain why the force control manipulator can sense the external force from the end effector? What are the sensors or what things you need to sense and to have the control?
We have no idea about this.
Okay, so basically, so in the position control, I think we have already done the forward kinematic and inverse kinematics. So the basic thing inside your joint is the encoder. So the encoder, they need, in position control, they need to know the position of each joint. And for the force control manipulator, you need to have the torque sensor inside your joint. So by a torque sensor inside each joint, then you can sense the end effector. So I think that will be our next lecture. We'll be talking about the stiffness and the statics modeling of the serial manipulator. Thank you. So I think this will be the end of our